Right, this is the lab for the force table. Actually, towards the end, there's something for Newton's third law. But this particular lab, the force table, is only about Newton's second law. So the following things I'm going to say, it's about forces that act on one object that pull in different directions. You add them up, that is the net force. Now here there's also a counterforce applied to it, so that there is a fourth force acting on the same object to put it into equilibrium so the thing isn't going anywhere. And all these forces add then up to the special case for Newton's second law, which is 0. So therefore the sum of the forces is 0, the acceleration is 0, it's not going anywhere. That's the force table. The easiest way to show Newton's second law, actually, because otherwise if you have something accelerating, it's really tough to measure. There is such an experiment, but it is a little tough to measure. So this one is the easy way out. Again, this is about Newton's second law, sum of the forces is the net force. All right, so here's the experiment, or the theory of it, the experimental procedure and the equipment needed. Then I'm going to get to the analysis right here. And here, this is the applet that I like you to use, and I believe it is this one here, this Desmos here, for the analysis. There's another one that works pretty well. It's this one here. It was actually tough to find these kinds of applets. Right. By the way, these links here will be in the lab, or are in the lab manual. The way they show up here on the screen, this might have changed in the meantime. I don't know. So anyway, so here's the data analysis. In the video, you will find data for all these setups, maybe even including the example. It's been a while since I taped that, so you will find all these data in there. Then you analyze them. One of the things to analyze is that the measured data are also supplied in the video, and the applet, that's the one that you would have to use in order to analyze that. All right, then in the video, these are some still photos with no sound. And you will see that people are pulling on these forces, on these spring scales, and again they come up with a net force that should come out to 0. Of course, it's a measurement, so it'll be close to, for example, in my example here, I came up with 12 newtons, which is relatively small compared to the 95 and 70 and 30 and so on. I had a 5% error on this one. So there will be some still images, and then at the very end there will be also some still images for Newton's third law. This is where you have two parties pulling against each other. But again, for the most part, this is about Newton's second law. You're just pulling on one object. All right, and that's it. And here come the videos. So here are all the masses at the correct angles. This is for the example, and that's what the lab manual shows. So the numbers, the angles here are correct. And now I'm going to lift the ring, and of course the ring is going to take off on me because of the 3 masses that are hanging on, or 3 weights. So I need a counterforce, which is this one here, and only one particular angle and one particular force works. So I have 55 degrees and 3.1 newtons. This is setup A. I double checked the masses and the angles according to the lab manual. Again, the ring here will just take off on me if I let go. So here is the counterforce. I teared this ahead of time. Okay, now I let go and I try to balance it, and again, only one angle will work. So if I try something else like this here or this here, it's just not going to work. It has to stay in the middle, and so again, just one angle works. I'm not touching that peg there, and I get 112 12 degrees and 3.0 newtons. This is setup B. I double checked the angles and the masses. Again, when I take the ring and I let go, it will just pull itself off. So I have the counterforce. I teared the spring scale before. And again, if I use some kind of arbitrary angle, it's just not going to work. The most heavy mass is over here, so I definitely have to pull this direction. So as I'm going to try to adjust this one here, and then again I don't actually touch the peg, but I need to read off the angle here accurately, so I come up with 44 degrees and 44 degrees and 3.9 newtons. So for the example and for setups A and B, we had 3 of these masses fixed. For setup C, we still have 2 masses fixed at certain angles, but the third one, the procedures say to take this one out, actually my procedures say so, and put it somewhere between 180 and 270 degrees. So let's say I'm going to put it here at 220 degrees. And this is where I hang the mass. And now, and this was my free choice. I chose that one. I chose 220 degrees. So now I'm going to see again, it's not possible for any angle to do it. It's only possible for one particular angle. So I'm going to hold it here and I'm going to come up with 80 degrees and 4.5 newtons. So this is setup D, which is free choice. So before I started filming, already set it up in such a way here. So I put this one at 0 degrees, I put this one at 295 degrees. I chose certain weights here, so 130 over here, and this one is 80 over here. This one here I had 125 to begin with. And the way it's set up, I think we can already see that this shouldn't work. This should definitely be pulling this way somewhat. So I'm going to put this one over to 140 degrees. And that's a little better. I think we can see that. And then I put a few more weights on here, masses. And then again, I did that before, and that's why right now it is being balanced nicely between the 3. I have a total here of 2, 3, 6, I believe 180 grams at 140 degrees. I don't need a spring scale for this because the instructions say just use 3 masses to balance each other. And when I compute that, when I measure it, I come up with, well, these are the 3 masses. This is the total force here. The total force should be 0.0 newtons because the whole thing is balanced. And there may be a certain angle when I make a computation with these masses here, but that angle has no meaning because the force is supposed to be 0.0 newtons anyway.